Hello everybody, hope you're having a good 4th 2020 day. Today I'd like to talk to you about the next iteration of the PC32 programming language environment. This version is called SS32 and it's tailored for distribution. It's mainly running on a C VM, but it can also run bare metal in hardware. This version was made to be a companion to the ARM PC32 version. It's called SS32 for 6-shooter. It's a 32-bit MISC minimal instruction set computer. It's word addressed and it has 6 instructions per word. These instructions are divided into 7 slots per execution cycle. We have 6 instructions that are executed and 1 fetch slot. As you can see, we have each instruction, each is 5 bits, and finally in the 6th cycle, or in the 7th cycle, we have a fetch instruction for the next cycle. So what in practice this gives us 0.85 instructions per cycle, which is not that good. It's a little bit less than the whole MIP. But the thing with this architecture is that you can actually skip that part. So call and jump instructions skip the penalty completely because they fetch the next instruction as they are called. So this gives us an execution of about 1.16 MIPS per cycle, but it gets averaged to about 1 MIP, so 1 instruction per cycle. So return knobs, shifts and loops also do this. So in normal execution you have an instruction, then a fetch, then an instruction. But if you have all the returns, the knobs and the shifts and the calls and the jumps, you get to skip that. So if you can see here, let me put the cursor here. If you can see here, skip execution, you get instruction, a call, the call fetches the next instruction and you get to skip the fetch phase. So it averages to 1 to 1 MIP, so 1 instruction per cycle. So it's entirely possible to run without any fetch penalty in many cases, most cases probably. Now this is the base instruction set. Each instruction is 5 bits, and the instructions here that are marked in spec here, these are the ones that skip the fetch instruction. These are the memory instructions. We have 2 registers, A and B, A for reading, B for storing. We have the I register, which is the top of the R stack, and we have the fetch A plus and store B plus. So you fetch A and you increase it by 1, you store in B and you increase B by 1. And our standard Forth words, we have do, drop, swap, over, add, and XOR, not, negate, and multiply. There is no subtract because you can just do negate and then add a word. There's also no divide, so that could be a problem for 3D stuff, but there might be a hardware solution for that. So now the main improvement in this version is the SMD instruction, which allows for an instruction change. So I am using this to explore multiple instruction sets, such as a SIMD instruction set, a GPU instruction set with sine, cosine, logarithm, square roots, exponentials, and also 8-bit, which is very important for addressing letters and such. So you know, for the block when I'm doing the editing, this is very important. So I can have pretty much any amount of instruction sets I want, because the SMD instruction takes the number that's encoded in the rest of the instruction to set the index of the instruction set. So let me show you a little bit of the SIMD instruction set, which is, I think, the most exciting part of this. So what I'm doing for the SIMD is that I am packing the stacks into vectors. So as you can see here, we have a normal and then a vector. So the normal stack is just 1, 2, 3, 4. That's just your standard linear stacking, but if you switch to a vector, let's say a vector 4, you will get the same 1 2 3 4 packed inside as if it were a single number. Now my current data stack is 16 deep, so I can have up to 4 vector 4s, and also the R stack would also behave like that, and the A and B registers will also behave like a vector of the size that you choose. So for example, I need to have multiple vector addressing modes. So for example, V1 will be 32-bit. Let's see here, and that will be the 32-bit, which is the normal execution, also called X32. There's also 64-bit, which will be vector 2, useful for 2D, and V3, which is 96 bits, which is very good for 3D because X, Y, and Z. There's also the B4, which would be the top of the line, the top of the memory lane width that you can access. Although maybe you could access the 512, but I don't think I can implement that in the FPGA. So switching modes, that's just one cycle per switch, so you can very easily just switch 3D stack as if it were a vector 3, vector 2, vector 1, vector 4, and so on and so forth. Now let's see an example of vectorized Forth with the vector 3. Here we have the normal execution. Let me tag it as a red word so I can go back quickly. We have normal execution, which is just normal execution. In this side we have the stack, the instruction, and on the other side we have what the stack looks like. So I push 1, I push 2, I do that 2, I have 2 to 1 in the stack. Now I add that 2, I have 4, and I add that, and I have a 5 as a result. Now, how would that work in a vector? So, well, first let me just push the number. So I push a 1, I push a 2, and I push a 3. I have a 3 to 1 on the data stack. Then I call my switch instruction, which is in this time will be vector 3. I switch to vector 3 mode. Now I do dup, and what you can see is that it's not duplicating just the 3, it's duplicating the entire vector. So now I have 2 vector 3s on top of the data stack. Now if I add, it will add as a vector, so I have a 6 and a 4 and a 2, and I switch back to X32, which is actually, well, it's just a vector 1. So this works for the math and the Forth opcodes. So the jumps and the loop are unaffected because, well, it doesn't make any sense to have like 3 numbers for a loop, or have like 3 numbers for a jump. It makes no sense. Now lit, the literal behaves by copying that number n times by the vector length. So if you have a vector 3 and you put let's say you put a 1 on the stack, that will result in 3 ones, so that one will be triplicated by the 3. So now we're the implementations. Well, this is obviously the software one. This is the one this presentation is running on. It's available on GitHub. You can see the address here, dscfproc/SS32. It's running mainly on Windows since I intended for distribution, so it's a bit slower than the original PC32 because that one was pure assembler. This one is C, and it's a bit, well, it's fairly slow because it's C. But you can get the executables in the release pages. I still have to implement the vector part of the instruction set, but it's looking very promising. Now in hardware, this is what I've been working on the site. It's what I like to call the little cell for the cell CPU, the one for the PS3, because it was very hard to handle, and it has a very similar ring bus architecture. So the little cell will run in an A100 Xilinx FPGA at around 100 MIPS, but it will have 32 cores, and each core will have its own memory space, but core 0 can access each core's memory spaces as if it were its own, so you don't have to use all 32 cores. You can use use the first core and just get a handle for the architecture as you learn and move on into whatever you're doing. That A100 chip has a lot of DSP, so it's possible to do the whole vector thing. And the cool thing is that you can access you can address memory in 20 to 28-bit addressing modes. So what I'm thinking is that I'm going to have 4 128-bit DMA lanes in a ring like the original PS3 cell, and about 1 triangle rasterizer per core, which is just trivial. If you do it in FPGA, it's just like 3 ads, and then you compare design and say, well, this is inside the triangle, this is not inside the triangle, but it's still in development. And well, now we come to the Bandit. Now I have 2 models. I have to split them for the time being. The first is the original, the ARM, the RP2350, which is the one that is in production currently. It runs at 250 megahertz. It's dual core. It has 4 megabytes of flash and it has 8 megabytes of battery back PSRAM. You can get it for pre-order. It's $169.99 plus the shipping, which is I think it's 20 bucks. You can get it on the here in the page dscf.co.uk/bandit. This one is coming along pretty well. I can't really show it today since I didn't make the slides and I'm still working on the drivers, but it's moving okay. Now the next one that I'm working on is the M.2, which you will be able to switch the cores by having each processor be an M.2 card you slot into the back of the keyboard. Now this is still in an iteration process, which is the little cell, this one here is the one I'm working on, so it needs a little bit more time before I can release it. But the base specs are looking pretty good. It's 100 megahertz, it's multi-core, it has 4 megabytes of flash, which you don't really get to use because that's the minimum space the FPGA definition needs. But you get 64 megabytes of SD RAM, or you can get 256 megabytes of DDR3 DRAM, but no promises on that. I'm still working on that. The layout is fairly complex for doing DDR3, so it needs a lot of iteration. So this is pretty much the news for me. Thank you very much for watching. I hope you have a great 4th 2020 day. You can always contact me at tight@dscf.co.uk. And if you have any questions, I don't know if my internet connection will be able to get to stay up for the Zoom meeting. It probably won't have any video, but I think I may get some audio. So if you have any questions, I'll try to be present in the presentation. Thank you very much, and I'll see you later.